Let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another exciting edition of Math 391, Differential Equations. Last week, very eventful. We had our first test, which I guess I want to begin by talking about that for a bit. Someone else come in. One thing I should know, where I should know that. Okay, so we'll fully solve this next time. But something that I do want to mention is take note of the regrade feature in grade scope, right? So if you did remember with grade scope, I did say that. I don't know. I don't even remember if I said this before. Feature on grade scope. Okay, so if you have, remember, so when the computer grades it, it doesn't give you partial credit. And so if you get one problem wrong, we had 20 problems on the test. So one problem is a loss of 5%, which might be a lot, right? You get two things wrong, you're down to a 90. Get three things wrong, you're no longer an A. So you might have situations, especially the ones where I ask you to scan and upload your work. If you think that you got something wrong, you lost the 5 points, but your scanned work shows that you understood more than you lost, you can submit a regrade request in GradeScope when you're reviewing your test. Probably the most efficient way to actually get me to look back over your test, because if you see me in office hours and you want me to look over your test and look at your scans and do I have to have open multiple screens to get that to work, and to have Zoom running while I'm doing this, it's really crazy. It's better that I do it when I'm not online with you guys. So send in regrade requests for anything that you think that you can get partial credits on, and I will look over them to see if you can get some of that 5 points back. This will also apply to questions where it was like select multiple choices. Depending on the selection that you make, I might give you some partial credit based on your selections, even though you might not have gotten all of them, but maybe you got the most important ones, and so I can give you some credit for the select all problems as well. So if you think you want some partial credit on some of the problems back, yeah, the best way to do that is to hit me up via this regrade request and just have a short note on why you think you deserve more credit. Hey, can you look at my scans? I think I did most of the problem correct. I just made this one mistake in this one line, and that's why I got the wrong answer. That is something that you should actually take into account and take advantage of. So that's the test. What I wanted to mention on the test. Let's actually jump back into it though. So today we're still going to keep things pretty light, pretty computational. There is some theoretical stuff that I know I've been promising you for a long time to go over. I think I want to go over that towards the end of this week though. For now, I still want to just keep things basically computational. We are going to talk about the remaining examples we have left for these guys, mechanical vibrations, the spring mass problems. Then we're actually going to move on to higher order equations. I'm going to show you how to solve those guys. I'm going to have to reteach you a lot of things, or maybe just remind you of a lot of things from pre-calculus actually, that are going to be useful in solving those types of problems. But before that, let's wrap up this section. I believe it's 3.7. By the way, 3.8, there's really nothing else for me to teach you regarding 3.8. 3.8 is called forced vibrations, and 3.8 basically just assumes that there is some external force in play, which means they literally just give you a function that you assume is the external force. And so on the right side of your equation, instead of like us, instead of having a 0 here, you would just put in that position whatever force you're told is there. And so 3.8 is really just the non-homogeneous version of what I'm teaching you now. I don't recall if I have examples like that, because they actually don't show up very often in like departmental finals. But 3.8 is just when you have a non-zero thing over here. And for that, they have to tell you what that thing is. So it's not even like something you have to figure out. They're going to tell you, here's the force, here's the external force being experienced by the system. And you just put that on the right side whenever they tell you the external force. So now we looked at the derivation last time, remind ourselves about some laws of physics, Hooke's law, Newton's first and third law, acceleration due to gravity, damping force, all that good stuff. Essentially, we had the following coming together. We can model the motion of a mass at the end of a vibrating spring by a second order linear differential equation with constant coefficients. It's homogeneous in the case that we do not have any external force acting on the system. It is a homogeneous equation in the sense that it's non-homogeneous when we do have an external force that we can track with some function. The initial position is given by u of 0, and the initial velocity is given by u prime of 0. Now, in that equation, when we have mu double prime, scroll down a little bit. When we have mu double prime plus gamma y, mu double prime plus gamma u prime plus ku equals some function. M stands for mass in that. That's what you need to remember. And you also need to remember the units that measure mass. One way to find mass, though, as you can see in the important things to keep in mind, is just to take the weight divided by the gravity. So if you're given the weight of the mass in pounds, you just divide that by the acceleration due to gravity, and that is going to give you what the mass is. That follows by Newton's first law. The gamma is the resistance force divided by velocity. A lot of people just thought it was resistance force. I saw some options where people were selecting the wrong term for that. That wasn't a bonus problem though, so that's neither here or there really, but it's resistance force over the velocity. So you talk about the force experienced by the system when it's moving at a certain velocity, take the force, divide by the velocity, and that gives you the gamma. Sometimes they tell you the gamma straight up, and you don't have to find it. The K in our equation is the spring constant. You can find that by taking the weight divided by the length that the spring is stretched by the weight. And that's how you can get that set up. So that's how you get the left side set up. While doing this, just make sure all your units are consistent. Also remember that the downward direction is the positive direction in this conceptualization. Your u of 0 equals 0 if we say something is released, or it's if we say something is at equilibrium position. U prime of 0 equals 0 if we say something is at released, or it starts from rest. That being said, not much else to say about that. To solve this is something that we know how to solve from before this section. It just comes down to solving a second order linear differential equation with constant coefficients, which hopefully by now we know how to do very well. So we did one example, and reduce the size a little bit so you can actually see. We did one example. So we were told that a 2-pound weight, that's your W, stretches the spring 6 inches. This tells you your L is 1/2. Because we're measuring it in feet, to a position y equals 0, that's the equilibrium position. Set up an initial value problem for the position of y of the spring being stretched down, 6 more inches, and release. This means u of 0 is another 1/2 foot. Released means your u prime of 0 was 0, starting from rest. So by knowing everything that I mentioned earlier in that box, you will know how to read the word problem and actually set these guys up. So we know that mass, the m, is the weight divided by gravity. So that was 2 pounds divided by 32 feet per second squared. That gives us 1/16. We know that the k, the spring constant was the weight divided by the length stretched, that is 2 divided by a half. And we know that gamma is 0. We know it's 0 because it's not mentioned. It's one of those things where it's like you neglect air resistance if it's not even mentioned, that you should pay attention to it. So we will see situations where we have to know the gamma. But essentially doing that, we could set up our initial value problem. Now, we are going to fully solve this. So while this question didn't really require it, let's actually finish solving this. All right, so how do we continue? So I have 1 over 16 y double prime plus 0 y prime plus 4y equals 0. How do I finish up? Find the characteristic equation. What does that look like? No. Right, 1 over 16. 1 over 16 r squared plus 4 equals 0. So now what you would have here is your r squared is equal to, you'd bring over the minus 4, and then you'd multiply by a 16. And then you take the square root. But there's a negative under the square root. So that's actually going to be 2 times 4. That's going to be 8 I plus or minus. So this tells us the solution looks like what? Plus or minus 8I. Right, that looks like C1 cosine, it's like C1 cosine 8t plus C2 sine 8t. Right. Now, here's one of the situations in which thinking in terms of complex numbers, you might think, well, these are imaginary numbers. Are these ever going to be useful in real life? What you can see here through Euler's equation, this actually makes a lot of sense in physical reality, this idea of a complex number. Because via Euler's equation, we get that sines and cosines come out of it. And that actually makes a lot of sense in what we're doing. Because the spring, if you look at the motion, unless you deform it, it's just going to keep vibrating. It's going to bounce up and down, not unlike sines and cosines. Now, it might not bounce up and down with a perfectly even kind of period or a perfectly odd kind of period, but it's a combination of the two. So this just kind of shows you, so we're oscillating. So having a complex answer as the root of an equation does give rise to some meaningful physical application. So that is what that looks like. Now, of course, we do have some initial conditions here. So let's actually take care of that. But that is true. This means we need to be able to find y prime, which in this case is going to be minus 8c1 sine 8t plus 8c2 cosine 8t, and y of 0 equals a half means that if I plug in 0 for t, I would get a half as the result. That would actually only leave me with c1, so my c1 is a half. I don't know why I wrote y1 here. That should be y prime. And if I have y prime of 0, I get 0. That tells me I get 0 on this side when I plug in 0 into this first part, and that would give me 8c2. So this actually means c2 equals 0. And so our solution finally looks like C1 cosine 8t. And that is how our thing is going to be oscillating up and down. Cosine 18, right? So you essentially have, if I look at the y, it's going to start at like a half. And it's going to bounce up and down from a half to, and keeps bouncing like that. So if you look at if you imagine what's going on here physically, you have the thing, you have the spring, it's attached to the mass, and it bounces up and down 6 inches above and below equilibrium. It keeps bouncing up and down like that. And this is, of course, an ideal scenario. It essentially seems like it will bounce up and down forever. Of course, you know that this is technically not true, but it's not true because we have other things like air resistance coming into play and all that stuff. But under neglect, if we imagine that there was no friction, there was no air resistance, nothing, nada, this thing would bounce up and down forever. And it will look like that until the heat death of the universe. But yeah, that is what it would look like. So we fully solved that equation. Let's do some other examples. And these are word problems. I think the main thing is to know how to set them up. Chances are, if you know how to set them up, you will know how to finish the problem. So it's just a matter of setup. So here's another one. A 4-pound weight stretches a spring 6 inches downward to a position where y equals 0. So I have an initial value problem. If the spring is lifted back up 6 inches and is released. This one is actually very similar to the other one, actually. So I'll just set this one up. So here, when you see a problem like this, you want to find the important guys. These are the m's, these are the gammas, and the k's. The m is going to be weight divided by gravity. So that's going to be 4 divided by 32, or so was it a 4 pounds? I want to make sure I didn't do a typo. It was 2 pounds last time. Okay, so we're good. So in this case, it's 4 pounds. So that's actually 1/8. And our gamma equals 0 because it's not mentioned. And our k is the weight over the length stretched, which is 4 divided by, it stretches 6 inches. So that's 8. And so now we can actually set these guys up. So it's 1/8 y double prime plus 0y prime plus 8y equals 0. And our initial position and initial velocity. All right, so why don't you guys tell me that? What is the initial position here, reading that question? Right, so we're told that the weight stretches the spring 6 inches down to a position y equals 0. So this is the stretched position. Then we're told the spring has been lifted back up 6 inches. So it's back up from a position y equals 0. So it's half a foot going in the upward direction. So that's actually -1/2 would be here. The initial velocity? 0. Right, so it says it's released. So yeah, that's it. So to set up this problem, that's what it would look like. Now, of course, to solve that, that shouldn't really be an issue. But we're just going to set that one up because it's actually pretty similar to the last one. Let's actually look at this one. It's a little more hefty. I don't know what's going on. Why can't I select this? Okay, there we go. I don't know what was going on before, but it seems we're back in business. Let's just go. All right, so read that. Make it a little bit bigger. And you are going to tell me how to set these guys up. You're going to find the M, you're going to find the gamma, and you're going to find the K. And you also want to tell me what your initial conditions are. Don't know what we want to use here. Maybe Y again. All right, so a mass with M equals 2 is connected to a spring with spring constant K equals 4. The damping is such that when the mass is traveling at a velocity of 1 foot per second, the resistance is 4 pounds of force. Suppose the mass starts at the equilibrium position with a downward velocity of 3 feet per second. Answer the following 2 questions. Find the general equation of motion for the system, which means you need to set up the differential equation. You need to solve the differential equation. All right, so M, right, they just kind of gave that to you, right? K, they also just gave it to you. They're literally like K equals 4. What about the gamma? It's 4. So remember, gamma is resistance force over velocity. So this is resistance force over velocity. And they told us the velocity is 1. When the velocity is 1, it experiences a resistance of 4 pounds. So that's our gamma. Y of 0, initial position? 0, because it starts at equilibrium. Initial velocity? Right, 3. Again, downward is the positive direction here. So it's positive 3. And that's actually going to be it. So to find the general solution, we're just going to first set up the equation. So it's 2y double prime plus 4y prime plus 4 equals 0, because we're not told any external force is acting on the object. So that's our guy with these initial conditions. Right, and they already saw what I was going to ask. So of course you'd start by going into the characteristic equation. I can actually reduce this by 2. And what's the solution to that going to be? Can we factor this? No, you can't factor. So you jump into the quadratic formula. Minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. Now, you can factor out a 4 from under this radical. It's going to be a 2 when you move it outside the radical. And then you'd have 1 minus 2 over here. So that is just going to be minus 1 under the radical, which is just I. So it's minus 2 plus or minus 2i all over 2. And so your r is minus 1 plus or minus I. This gives us an equation. What? No, all are positive? What do you mean? Oh, you mean you were answering my question as to why we can't factor? All are positive does not necessarily mean we can't factor. There are things that we can factor that they're not all positive, like r squared plus 5r plus 6 can be factored. But it's hard. The numbers just didn't work out. So here, we know how to set this guy up. It's C1 e to the minus t cosine t plus C2 e to the minus t sine t. Of course, remember, try to guess what the answer is before I even write it down. Some of you actually did that, which is good. You do want to take an active learning approach here, remember. So that's our guy. Of course, we know we're going to need to find the derivative because we're going to plug in the initial conditions. So this is going to be, we're going to do two versions of the product rule here. So for the first part, differentiate the exponential, leave the cosine, plus leave the exponential, differentiate the cosine. Then differentiate the exponential, leave the sine, plus leave the exponential, differentiate the cosine, the sine to get cosine. Now we know that y of 0 equals 0, so that means that C1 equals 0 right away. Because the sine of 0 is going to be 0, so it kills that entire term. Cosine of 0 is 1. E to the 0 is also 1, and so we're just left with C1 on that side. So C1 equals 0. Our y prime of 0 was 3. So now we go y prime of 0 equals 3. This means I get 3 on the left side when I plug in 0 on the right side. And again, all the sine functions go to 0. So this is going to 0, that's going to 0, this is going to 0. And the cosines are going to give me 1. I also now know that my C1 is 0 by this guy. And so what am I finally left over with? I just have C2 by itself. So it's 3. So ultimately, the thing that's modeling this equation is going to be 3 e to the minus t sine t. And that's the answer for A, for part A, or part 1. Now we are at part 2. It doesn't matter technically if you use x or t as the independent variable because it's not really mentioned in the problem. T is a little bit more intuitive here because we are talking about feet per second and things of that sort. So time is definitely a factor here. So it doesn't matter unless the problem stated it before. But I'm using t because we're thinking in terms of time here. And in fact, part 2 says, after 1 second, if you held your hand 2 feet below the weight starting position, would the weight eventually hit your hand? What do you guys think? So this is measuring the function. After 1 second, what is going to be our position? No. We pretty much want what? We pretty much want y of 1 is going to be our position. That's going to be 3e to the minus 1 sine of 1. And so now what you're going to want to realize is that's actually, that is going to actually be less than 1. I don't know exactly what it's going to be, but the most sine of 1 is going to be less than 1 for sure, because sine of it, you need sine of pi over 2 to hit 1. So your sine is increasing on the way up to 1. So it's not at 1 yet. So it's probably around 0.8, 0.9. And then we're multiplying by something that's roughly 1 because e is 2.7. So 3 divided by 2.7 is slightly bigger than 1. And then we're multiplying by something like that. So it's less than 1, or it's at most 1. It's not going to be bigger than that. So now, with that being said, also, the e to the minus t decreases. Hopefully you realize that. Decreases the amplitude over time, right? Because the e to the minus, the sign is bouncing up between plus or minus 1, but the e to the minus t is actually damping the motion. If you look at what the graph of something like this would look like, it's bounded by right? So this guy here is going to be your e to the minus t. This guy is going to be your minus e to the minus t for when your sine function hits negative. And your graph starts out at 0 because the sine of 0 is 0. And then it bounces up and down. But it bounces up and down bounded by the exponential. So now you're in a situation where the spring starts oscillating to a larger degree in the beginning, but it starts it starts to like go to rest, right? So it starts oscillating quickly, boom, 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 boom. Then it slows down, right? That's what this is modeling, right? Which is a more realistic situation. Again, the complex numbers brought up into a physical, it coincides with something that we would see happening in physical reality very nicely. So if you want to show something is oscillating, but it's oscillating less and less over time, which is what you'd probably expect a vibrating spring to behave like, unless you're acting out with an external force, an exponential with a negative power times a sine function or a cosine function is actually a pretty good model. And so my answer would be no. It won't hit your hand. And if you want to be a little bit more careful, this I don't believe is less than 1, but for sure it's less than 2. We can say that for sure. That much should be clear. A little bit less guesswork into that. So it's not going to reach more than 2 units below equilibrium after a while, because your e to the minus t is actually dampening the motion. Which again, now kind of makes sense why they call it damping coefficient. This guy had a middle term that are some of the other guys we were looking at did not. So that's that. And that's one of the harder one of these problems I've seen when they ask a question like that, where you kind of had to do some sort of estimation in your head. Let's move on to another example. All right. So at this point, help me out again. Tell me what the M is, tell me what the gamma is, tell me what the K is, tell me what they're using U's this time. U of 0 and U prime of 0. So a 4-pound weight in its equilibrium position stretches a spring from which it's suspended by a half a foot. Beginning in its equilibrium position, the weight is given an initial velocity of 4 feet per second downwards. Air resistance, which is proportional to velocity, is 8 pounds when the weight has a velocity of 8 feet per second. Find a function u of t which describes the displacement in feet of the weight t seconds after its release. So here they're giving you all the variables they want you to use. So to answer a previous question earlier, in this situation, you definitely want to use t. And you want to use u for the dependent variable, and t is your independent variable here. They even gave you gravity. That's very nice of them. Assume the acceleration due to gravity is 32 feet per second squared. That's the question. Tell me the numbers. What is the m? 1/8. So remember, m here, they didn't tell you right away, but you know that it should be weight over gravity because of Newton's first law, right? Weight is equal to mass times gravity because force is equal to mass times acceleration. So this is 4 divided by 32, so it's 1/8. What about the gamma? Right, it's 1 because it's experiences a force of 8 pounds when we are moving at 8 feet per second. Resistance force divided by velocity is just 8 divided by 8, so that's your gamma. So here, we figured out m by looking at the 4 pounds weight and the fact that gravity is 32 feet per second. We figured out the gamma by realizing that it's 8 pounds when the velocity is 8. We are going to figure out the k by doing what? What is k? I think it's 8. So remember, this is weight over the length stretch. The weight was 4, the length stretch is 1/2, and so this is 8. And so, yeah, we know that that's 8 because of this 1/2 a foot that's mentioned here, as well as, again, this 4 that's mentioned here. So that's how you read the problem, come up with the numbers. Initial position. So it says beginning in its equilibrium position, which means 0. The weight is given an initial velocity of 4 feet per second downwards. So the initial velocity, is what here? Right, it's 4. And now basically you can set this up. Find a function u which describes the displacement, blah, blah, blah. Okay, so at this point, again, this is all previous material. So write this out in your notes. Try to keep one step ahead of me. I'll write a little bit. Come again? How's it for? It says here, initial velocity is 4 feet per second downwards, right there. All right, so now you guys start solving the problem. I'm going to just do it now, but try to stay like one step ahead of me. You can probably even ignore me, what I'm saying for the moment, and get through the whole problem, at least, a couple seconds before me, and then you can look back to see if you actually did, if we're getting the same thing. So this starts out looking like 1/8 u double prime plus u prime plus 8u equals 0. So I can multiply by 8. I don't think that factors. Okay, so that's what I got for the general solution. Do you guys agree, or did I make a mistake? Before you go through and solve for the particular solution. Are we all on the same page so far? Yes, no, maybe so. Okay, well, interest there. Okay, let's move on. So we know that y of 0, let's actually just find the derivative right away. So my y prime is going to look like so y of 0 equals 0, I believe it was. Y of 0 equals 0, and then y prime of 0 was 4. This means your C1 is 0. And so here we would have 0 here, we'd have 0 here. We'd have 0 here because of the sign, 0 here. So y, or I should be using u's. So u of t equals 1 over. Okay, so that's what I got. Do we agree? Okay, great. I think I had one more problem somewhere here. Oh geez, we have 2 more problems. We're looking at B here. I mean, personally, I think this is already enough practice, but let's actually just beat the horse to death. So for this one, this is something I will actually teach about in chapter 5, actually. So 10 part A, it's a little bit above our pay grade at the moment. But part B, we should know how to do. So there, read the question. And again, try to actually start it a little bit before me. Maybe you can even turn down the volume or just wait for me to say, did you get the same thing? And then you can look up. But actually try to get through the problem by yourself, from the setup all the way down. So a mass is weighing 2 pounds, stretches a spring 6 inches. They love those numbers, as you can see. The mass is pulled down 3 inches and given an upward velocity of 1 feet per second. Find u of t. the displacement of the mass in feet from its equilibrium position at time t after release. Assume that the acceleration due to gravity is 32 feet per second squared. All right, get started. I'll give you guys 10-second head start, and I'll be right behind you, and you can see if you're actually getting what I'm getting. All right, I'm going to start now. So hopefully you've already started. Okay, is that what you guys got? Did you guys finish already? So the equation I got was 1/16 u double prime plus 4u equals 0. The initial position is 3, and the initial velocity is -1. It's -1 because it's with an initial upward velocity of 1, so the up is the negative direction. Of course, that leads to this characteristic equation. I got plus or minus 8i for the roots. This leads us to C1 cosine 8t plus C2 sine 8t for the general solution. To find the particular solution, I found the derivative, and then I plugged in the initial conditions, ended up with getting C1 equals 3 and C2 equals -1/8. And so my function is u equals 3 cosine 8t minus 1/8 sine 8t. Hopefully you got that or something similar. A couple of people seem to be getting the same thing. All right, last question. Spring has a spring constant of 8. A 4-pound weight is pulled down half a foot below equilibrium, then given an upward velocity of 5 feet per second. The damping constant is 2. Assume the acceleration to gravity is 32 feet per second squared. Solve for u of t. Find the distance of the weight from the equilibrium at t equals 1 second. So again, give you guys like a 10 or 15-second head start. Just try to stay one step ahead of me. No, you don't have to be farther than that at this point. And just see if we get the same thing. All right, I'm going to start now. So So I got the answer to part A here. Do you guys agree with that? Right, so I got 1/2 e to the minus 8t plus 9t e to the minus 8t. Now to answer the second question, it says find the distance of the weight from the equilibrium position at t equals 1. Let me just plug in t equals 1 there. No, you got something different for the U. What did you plug in for U prime of 0? It was -5. U prime of 0 equals -5. Did you have that? Oh, here I had +5. So that should actually be a -1. And that should be well, I would have -5 is equal to -4 plus C2. So I would add 4 to both sides. So that's why the 4 becomes a -1. The -5 plus 4 would become the -1. So that's Incha keeping us honest. And yeah, at least at this point. I think we kind of beat this kind of problem to death. I'm starting to get bored with it, but yeah, that's good enough for now. So as you see, I was looking at a bunch of finals. None of them really deal with the 3.8 section. 3.8 is literally they're going to have a sentence that tells you, oh, there's an external force of this. And then you'd put it on the outside there. But I don't see that being asked very often. I can't actually remember recently any final that actually asked about that. But that's what 3.8 is about. You'll see stuff like that in your homework. But it just comes down to doing this. And on top of it now, you have to do like the undetermined coefficients stuff. And in this case, you'll tend to see undetermined coefficients because they're always going to make the function look like a sine or a cosine or an exponential times a sine or a cosine, because that's what would match up mostly with physical reality. And I think that's all we have left there. So one thing, let me just make a note here for when you guys are reviewing the notes. So we started here on on 6:30. Okay, just so we know where we actually picked up. All right, now let's actually change gears because I'm kind of bored with this topic at the moment. Hopefully you guys found that okay. New main topic, which we're going to cover for today. It's going to spill in a little bit of tomorrow, and maybe even tomorrow we can start our theoretical discussion of seeing why things kind of work out the way they do in the universe of differential equations. So in this chapter, we're going to discuss higher order linear differential equations. That's what chapter 4 is actually about. It's actually a much shorter chapter because it's the same intuition and the processes that you would have done for second order linear differential equations. The same kind of ideas would work for higher order linear differential equations. So these usually refer to differential equations that are third order or higher, right? So that you have a third derivative or higher. However, in principle, you kind of deal with them exactly the same way. So chapter 4 ends up being really short, and it just comes down to, they just give you some higher versions of formulas, which in fact, I already gave you. So for example, when I was covering variation of parameters, I gave you the formula for the nth order case before even giving you the formula for the second order case. So this is the nth order variation of parameters. They spoke about that in chapter 4. I already told you guys that. This they mentioned in chapter 2, and they didn't mention the other one, but I already mentioned. There are a lot of things that I have already mentioned that you would already know here, specifically towards higher order. I just want to remind you of some of those things and then jump into it. The difference between the higher order and the second order is the polynomial that you get for your characteristic equation. The polynomial will have the same degree as your highest derivative, as the same as your order of the differential equation. And so what you'd realize now is you don't have to just solve quadratic equations. You have to solve cubics, quartics, quintics, maybe some things higher. And so if you just supplement your knowledge by reminding yourself about how to factor higher degree polynomials, then you're automatically kind of already know how chapter 4 is going to work. Let's just go through some quick reminders though, some things that I put in a box because I want to make sure they should always kind of be at the forefront of your mind, more or less. So an Order Linear ODE is one of this form. This is a non-homogeneous case. When my n, the order is greater than 2, we call it a higher order linear differential equation, which we'll short for HOLDE. If your g is 0, we call it a homogeneous equation, and it would look like the following. By the existence and uniqueness theorem, we know that if all the coefficients, the p's and the g's, are continuous on some open interval I, then on that interval, we can find a unique solution to this differential equation that satisfies any list of initial conditions we are given. This solution will also be n times differentiable, and it will have this form, right? So there's going to be a homogeneous component to it, as well as there's going to be a particular solution component to it called the yp. The c1y1 plus c2y2 dot 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 c and yn, these are the homogeneous solutions. These are the solutions to the equation number 2, and it's called the homogeneous solution. The sum of the particular solution and the homogeneous solution, that's called the general solution. And it's called general because any solution to the differential equation can be written in this form. No matter if someone else finds maybe a slightly different list of functions, or they chose a slightly different particular solution of slightly different fixed points to base everything off of, you would be able to simplify their answer to look like your answer, and even if both of you did the question separately, right? What else do we need to know? These solutions of the homogeneous, there must be n linearly independent solutions to a homogeneous nth order linear differential equation. Saying that they're linearly independent means if you set up this equation, c1y1 plus c2y2 plus dot dot dot, all the way up to c and yn, the only solution for that is the trivial solution, namely all the coefficients must be 0. Another thing this means is that the Wronskian is not 0 on the open interval. The Wronskian, remember, is when you line up all your functions along the first row, and then you take n minus 1 derivatives of those to create an n by n matrix. The determinant of that matrix is the Wronskian. Abel's formula tells us we can find the Wronskian by it's going to be some constant times an exponential raised to the negative integral of the coefficient of the n minus first derivative, right? So find the guy who's 1 less, the one below the highest power, the highest order, take his coefficient. If you integrate that, put a negative sign in front of it, raise it in an exponential, multiply by a constant, you get the form of the Wronskian. That is by the generalized Abel's formula. We also have variation of parameters, still works. That's the formula. I just remind you here. I remind you what the W and the WI are here as well. And that's just a way to find the YP. So we'd find the Y1, Y2, Y3, all the way up to Yn, very similar to how we did it before for second order, right? You find the characteristic, find the roots of the characteristic equation, and then after assuming the answer looks like e to the RT, you can get through that. Undetermined coefficients is another way, but again, it works in very specific circumstances. It works if your g is a polynomial or a trig function, sine or cosine specifically, or an exponential function, e to RT, or a polynomial times an exponential, or a polynomial times a sine, or a polynomial times a cosine, or a polynomial times an exponential times a sine, or a polynomial times an exponential times a cosine, or a sum of such terms. That's when you can use undetermined coefficients. Now, of course, the process for solving it, very similar. Given this guy, where the AI are constants, so you're talking about homogeneous constant coefficients scenario, you assume the solution looks like y equals e to the rt, because that is a function that would be self-similar to all its derivatives. So you can, it's very intuitive that the left side is going to cancel each other out and to give us 0. Potentially, the exponential is the best function to do that. One obtains a characteristic equation, which is now an nth degree polynomial. Solve the equation for R. You should have n solutions counting multiplicity. Why doesn't it work for x to the minus 100? Because that's not a polynomial. Because x to the minus 100 is actually 1 over x to the 100. It's a rational function. It's not a polynomial. So it doesn't work. So yeah, that was something that was on the test. I was asking you, would undetermined coefficients work for this guy or blah, blah, blah? Right, so it only works for the cases I mentioned before. Polynomials, polynomials times sine, polynomials times cosine, polynomials times exponentials, polynomial times exponential times sine, polynomial times exponential times cosine. X to the minus 100 is not a polynomial. All right, once the roots of the characteristic equations are found, you build the solution using the process that we did for Soldes, which means if there's repeated roots, you know, you count up to the multiplicity by multiplying by t's until you exhaust the highest power. If they're distinct roots, you just put e to the distinct root times t in the power if it's real. If you get complex roots, it splits into sines and cosines, potentially multiplied by exponentials based on Euler's equations. So again, we really know how to deal with all of this. I just wanted to put at a glance some things that you want to remember and keep at the forefront of your mind. At this point, you might be thinking, well, that's actually not so bad. Technically, you don't have to teach us anything here, Jhevon, because we already know how to do all this stuff. Well, not so fast. See, what makes higher order differential equations harder is the characteristic equation part. Having to solve the roots of a characteristic equation. You see, a long time ago, very young mathematician, very passionate mathematician. He has a very interesting life story. He died very young. Legend has it, in a duel over a girl. Because mathematicians love hard. And the night before the duel, when he realized he was in over his head and he probably wasn't going to live past the next day, he wrote down a lot of his mathematical musings in his notebook. And for centuries later, mathematicians have been digging up the treasures of what he wrote in those notes. Among other things, one thing he wrote in his notes, the mathematician by the name was Galois, Évariste Galois, a French mathematician. He wrote, you know what? Any polynomial of degree 5 or higher, there is no general formula to find the roots. So it turns out we have a quadratic formula. We have a formula to find all the roots for a quadratic. We have a cubic formula. Most people don't know it because it gets large and it gets messy. We have a quartic formula. So we have something of degree 4. There's a straightforward formula to find that that's equivalent to the quadratic formula just for higher dimensions. That one's even bigger and uglier. However, Galois figured out that once you hit degree 5, this was no longer true. There is no general formula. And so it turns out solving a polynomial, finding the roots of a polynomial of degree 5 or higher is in general quite difficult. It is actually impossible for you to write down the answer by hand. And you come to a situation where a lot of times you have to actually approximate the polynomial, the roots. You have to use some sort of numerical methods, techniques to figure out what the roots are, get close to them. And you can find the roots oftentimes to any degree of accuracy you want, but you can't actually just find the entire root as a whole because it's just such a formula, such a solution does not exist. Okay. Now, of course, in this class, we are not teaching you about numerical methods. That is a whole other class. And so in this class, what's going to happen is you're going to have a higher order differential equations, but they're going to be equations where you can actually use some special techniques with them. And so what I'm going to do for you in the rest of today's class is just go through some of these special techniques that you can expect to see pop up. So special case number 1, there are times when you will actually see, yeah, Pascal's triangle, we're gonna talk about that. Did you actually see that when I was scrolling? All right, that's a good eye because I thought I scrolled past that really quickly. Yeah, so special case number one is we can think of the characteristic equation as one of a lower power. For example, in this example, but I think these guys are going to actually get in the way. So let me move some of these out of the way. Yes, there is Pascal's triangle. And the binomial theorem. That really helps you figure out what the expansion of a binomial is. But the idea is, because the factoring is the opposite of expanding, if you know how to expand something, you automatically kind of know how to factor the thing that would look like its expansion. So it's one of those things that you'll have. Of course, Euler's formula and the polar form of a complex number is going to show up here. We actually derived some of these guys earlier. For some reason, to highlight all these guys, it takes forever. But yeah, we're seeing a very slow preview of where we're heading. And is example 11 the last example? I believe it's the last example. Right. So we'll move these guys to the side and we'll deal with them later. All right, so here's the first special case. So here you'll notice that it's a fourth order differential equation. The highest derivative is 2. However, notice that you can actually think of this as a lower order differential equation. Notice here, if we jump into the characteristic equation, it looks like an r to the fourth. However, the idea is, if you think of r squared as your variable, you'll notice that what you have is something that looks actually like a quadratic. So while it's technically a power 4, you can actually think of it as something which is a power 2. Right? So this is one way that it can happen. So for example, if the highest derivative, if I had the same question where the highest derivative was 6, and then the second highest derivative that you saw was 3, you could do the same thing here where you would have an r cubed in the place of the r squared that I have. So here, it is quartic, but I can think of it as a quadratic. So that's what I mean by thinking of it as a lower power. This is a quartic. But we can think of it as a quadratic. Right, so while it's a quartic, we can just actually apply this like a quadratic. So this means, do these guys factor? So a 3 and a 1 is what you'd want, and then you do a -3 and a +1, and that's going to work. And you'd have just, instead of r, you'd have an r squared here. But in principle, you could factor that just like a quadratic. And so what you'll have is you'll have 2 roots from the first part, r1 and 2 is just going to be plus or minus radical 3. And then your r3 and 4 is going to be plus or minus I. I want you to note we have 4 solutions. And of course, it's up to multiplicity, but there should be 4 distinct guys that you want to see. Now, multiplicity. However, here, no repeated roots here. So we have 4 bona fide solutions out in the open. But if you have a 4th order, you need to make sure that you're getting 4th solutions. We have to have that. And again, yes, that's something that theoretically I have to justify a little bit more than I have done. But at this point, to just know that and run with it is fine. How you would then finish this up And let's just see if your intuition is working. So given that those are my 4 solutions, what do you think the general solution is going to look like here for the homogeneous case? Right, so these are my 4 solutions. What is a homogeneous solution? What is the homogeneous solution going to look like? Go ahead, hazard a guess. Chances are you got the right thing. Yeah, C1 cosine t, C2 sine t, C3 e to the square root of t, C4. No, you messed up on the last part. Radical 3 is not a repeated root. There's a +1, there's a plus radical 3, and there's a minus radical 3. It's not a repeated root. Right, there's a plus or a minus. So here it's like a C1 e to the radical 3t plus a C2 e to the minus radical 3t plus a C3 cosine t plus a C4 sine t. Right, so that's how you do that, right? So nothing, actually, in principle, there's nothing really new to teach you here, right? You get the characteristic, you solve for the roots, and then you plug it into the general formula that I mentioned before with e to the RT. That is no different than what we did before. The thing is just being able to solve for the roots for a quartic in general can be very difficult, and you have to watch out for that. But yeah, that's it. So sometimes you see a special case, you have a higher order thing, but you can actually think of it as a lower order thing. Something like y to the 6th prime minus 2y triple prime minus 3y equals 0 would be dealt with very similarly. Right, so because that, again, it's a technically the polynomial will be of order degree 6, but you can actually think of it like a quadratic because the highest power will be double the middle power, and then you'd have a constant, right? Whenever you have the highest power being double the next power, and then the other term is a constant, you can think of that as a quadratic in general. So, yeah. Other special cases, when you have special factoring going on. So I'm talking about things like difference of squares, sum and difference of cubes, factoring by grouping, all these special factoring techniques that you learned about, again, way back in pre-calc, they come into play here. And that leads us to these examples over here. So that's special case number 2 that you might see. So sometimes you can think of something that's a higher order as a lower order. Sometimes you would have special factoring techniques. Now, I will mention here, we will see another way to look at examples 2 and 3 here. But that being said, let's actually just jump into them. So that's example 2. So, for example, I jump into example 2. What do? Well, this is going to be r cubed plus 1 equals 0. Now, one way I can think of that is this is r cubed plus 1 cubed equals 0. That reminds me of the sum of two cubes. It's like my a is r and my b is 1. Therefore, I know that this guy factors. This is going to factor into r plus 1 times r squared minus r plus 1 equals 0. So now this leaves me with r equals minus 1. The second part is going to be done using, it's a quadratic. You'll realize that it doesn't factor. So you'll jump into quadratic formula. Minus b plus or minus the square root of b squared minus 4ac all over 2a. You would end up with 1 plus or minus radical 3i over 2. And so you have 1/2 plus or minus radical 3 over 2i. That would give you 3 solutions, right? So this is your R1, your R2 and 3 are given by that. And then at this point, you know that that's going to be the guy. So there's that one. And that's just you noticing, hey, I can actually use a sum of cubes formula to factor that guy. So it comes down to you having to remember all those formulas. Remember, Winnie, remember, Winnie, remember. Okay. So yeah, the rest of this class, there is some new stuff I'm going to talk about, quote unquote new stuff, but the majority of what we need to know to deal with chapter 4 is to remind ourselves of all these things that we learned once upon a time in pre-calc, but it's been forever since we've done them. So example 3, similar situation. And by the way, we'll look at this another way later on. Not sure if I'll get to that by the end of today, but by tomorrow for sure. Again, you do this, you realize that you'll get r to the 4th minus 16 equals 0. You can think of this as a square. Again, you're thinking of it as a lower power, but at the same time now, you think of it as a difference of squares. So then you would end up with r squared minus 4 and r squared plus 4. This factors even further into r minus 2 times r plus 2, again by the difference of squares. You can't really factor this unless you do it over the complex numbers. But right, so this is going to give us r equals 2. This is going to give us r equals minus 2. This is going to give us r equals plus or minus 2i. So then ry equals c1 e to the 2t plus c2 e to the minus 2t plus c3 cosine 2t plus c4 sine 2t. Notice that I have 4 linearly independent solutions for a 4th order. Okay? So that's how you'd solve that one. I mean, I'm moving kind of fast here, but it's because I kind of expect you guys to remember this stuff from like pre-calc. But if I'm moving too fast, let me know. For this one, your characters will look like r cubed minus 2r squared minus r plus 2 equals 0. Hopefully you see this right away. If not, let me remind you how you'd look at this. It has 4 terms in it. You would think factor by grouping. So if you factor out the common r squared out of the first 2 terms, factor out a common negative sign out of the last 2 terms, you'll notice that you are left over with r minus 2 in both terms. So now you factor that out, that's a common term, and you'd be left with r squared minus 1. So this leaves you with r minus 2, r minus 1, r plus 1 is how that would factor by grouping. And so that gives you the 3 solutions: r equals 2, r equals 1, r equals minus 1, leading us to c1 e to the 2t, c2 e to the t, c3 e to the minus t as the general solution. And you could figure that out just by realizing characteristic equation, same old deal. Just now we have 4 terms. Factor by groupings should be one of the first things to pop into your head. So you factor out a common term from the first 2 terms, and then you see if that works. If that doesn't work, there's probably another technique that I'm eventually going to show you here. What else do we have? Special case 3. So let's talk about that whole Pascal's triangle thing and the binomial formula. Long division is coming back, throwback. Yeah, so there's something called the binomial theorem. Again, something you would have seen in something like an algebra class or a pre-calc class. It tells us how to expand a binomial, right? So if you have a plus b raised to the n or something like that, you expand it based on this formula where the coefficients are given by that. This is the theorem, for example, that tells us how to expand x plus y to the 4th, for example. It gives you this. Now, there's something called Pascal's triangle, which helps you to remember this pattern in a more of a diagrammatic way as opposed to a formulaic way. So you start out by actually forming the triune of ones, the triangle of ones right here. And then you can fill out each subsequent line by always starting with a 1. You always start with a 1 and you always end with a 1. However, for intermediate numbers, you add the 2 numbers above it to get that number. So for example, if I add the 1 and the 1, I would get 2. Moving down a line, if I add 1 and the 2, I would get 3. If I add the 2 and the 1, I would get 3. If I had the 1 and the 3, I would get 4. If I had the 3 and the 3, I would get 6. If I had the 3 and the 1, I would get 4. Down here, if I had the 1 and the 4, I would get 5. If I had the 4 and the 6, I would get 10. If I had the 6 and the 4, I would get 10. 4 and the 1 would give me 5 and 1. And you can go on and continue. So the next line would look like 1, 6, 15, 20, 15, 6, 1. What would the next line look like? Someone type it up, see if I get if you get the formula. What will be the next line? Right, so you'd have 1, 7, 21, 35, 35, 21, 7, 1. So for example, that is to say that if I were to expand a plus b raised to the 7th power, the coefficients would be 1, 7, 21, 35, 35, 21, 7, and 1. And how it would actually, how you would build the pieces together here is that you would actually start with the A at the highest power and count down. So it's A7, A6, A5, A4, A3, A2, A1, and A to the 0. And then you start with a B and you count up. So that you start with B to the 0, then B to the 1, then B squared, then B cubed, then B to the 4th, then B to the 5th, then B to the 6th, then B to the 7. And then you add all these guys together. Plus, 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 plus. And that's how you expand it to the 7th. Now, why do I care about expanding? Well, you don't really care about expanding. You care about going the other way. To go from this to that, to go from the right side to the left side, that is what we call factoring. Factoring is the opposite of expanding, which means if I know a theorem that tells me how to expand stuff, then I automatically will kind of know how to collapse stuff and factor stuff as well, just by taking that theorem and running it backwards. And so there are times when we are going to notice a pattern like this. We're going to notice that the coefficients are kind of lining up with this triangle. And then we're going to realize, oh, that came from someone expanding a binomial. And then we can undo that and get backwards. So for example, here, notice this. If I were to jump straight into the characteristic equation, r cubed minus 3r squared plus 3r minus 1 equals 0. And then I pay attention to the coefficients. Notice that this is a 1, 3, 3, 1. So this looks like a 1, 3, 3, 1. And you realize it reminds me of the third line in Pascal's triangle. Then you realize that the signs actually change. You start with a +1, then a -3, then a +3, then a -1. And then you just say, to alternate signs, make the second term negative to alternate the sign. So notice that if here, what's really going on, it's actually expanding a cube. If I have r plus 1 cubed, that would give me r cubed plus 3r squared plus 3r plus 1. However, if I have r minus 1 cubed, then I would have r cubed minus 3r squared plus 3r minus 1. Just by realizing, just by expanding the binomial formula. Because this guy, because this guy would look like 1, 3, 3, 1. And then you would put in the r cubed, the r squared, the r. Then you would put in the -1 to the 0. This here would be r to the 0. Then you would put in -1. Then you put in -1 squared, then you put in -1 cubed. And then when you put in the -1, that's what makes this sign negative, right? So even though initially you're like adding these guys together, this guy here is going to change all the signs in the middle. And so what you realize is that this kind of looks like r cubed minus 3r squared plus 3r minus 1, which is what you had, which is what we have. And so I realize that if that is my characteristic equation, I actually know how to factor it, but just by looking at it backwards. This means this factors into r minus 1 all cubed, which means it's a repeated root. My first, second, and third solution is 1, which means my solution is going to look like C1, e to the t plus c2t e to the t plus c3t squared e to the t. And so just by knowing Pascal's triangle very well, oftentimes I'll be able to see the pattern that's provided by this triangle in the coefficients, and then I'd be able to collapse it into a binomial and then expand it from, and then solve for the R from there. So that's a special case number 3. Every now and then you'll see like a binomial expansion popping up. Was there another? Okay. Now, long division. Okay, so this one is going to take a little bit longer, so I'll stop here for now. I'll leave these notes in the file, so you guys can read through this. Maybe try doing some of these problems for tomorrow, so you won't have to actually. So it'll go by a lot smoother. You'll know if you have questions ahead of time. So actually try these for tomorrow. So you're going to try these for tomorrow. We'll pick up with doing them. We'll finish this tomorrow, and maybe we'll start talking about some theoretical underpinnings of all this stuff. I will just leave this here. So try reading through this stuff. Again, special case 4 is also something you would have done in pre-calc, so you can probably read through that on your own and actually figure out these guys. Roots of unity. So this is technically a little bit new, but it is an application of Euler's equation, which I derived for you, I don't know, 3 or 4 classes ago. It's hard to tell. So basically, because we derived this, we realized that we can add 2n pi to the power, and it doesn't change the value. So you're going to use the right sides of these guys here, and you're going to actually swap them in place of your complex number. Well, the right side over here, and you're going to use that to be able to solve it. Now, if this section kind of throws you for a loop, it's okay. We'll talk about it tomorrow because it is technically kind of new stuff. But the special case number 4 shouldn't be too new. You should be able to figure that out. So try those for tomorrow. It's 1m, isn't it? And for now, we'll actually just, we'll stop there. Oh, yeah, awesome. Okay, good. There are other ways to do it, but I'm going to show you the nice way. So when you were doing it in the homework, if you wanted to do it directly, there were other ways to do it. But I'm going to show you the nicer way to do those. So yeah, there were some homework problems that required you to know how to not do this exactly necessarily, but do something similar to it. So you could do it with algebra, it would have taken you a lot longer. We're going to look at a nicer way to do it. But yeah, I think there was a homework where you were asked to do solve equations like this before. That being said, we are going to stop there. Hopefully that wasn't too bad. Like it's a light class, roughly speaking. And so it shouldn't have been too bad. So we'll stop there. I will see you guys in the next one tomorrow. Try those problems and you can actually see if our answers coincide tomorrow. And after that, we will talk about some theoretical stuff to kind of end out the week. Next week, we'll start on chapter 5, where we start to use series solutions. Yay! So probably a good thing for you to do this weekend is to just look over series, the basics of series. You can't hear me? Can everyone else hear me? Can you guys hear me? Okay, so I think it's you, Insha. For everyone, look over the basics of series and just remind yourself what they are, what a radius of convergence is, all that good stuff. That's going to be what we're going to jump into next week. That's chapter 5. It turns out to deal with the non-constant coefficients case is hard in general. What we tend to want to do is to actually use a series to help us, because finding a nice formulaic way to do it just doesn't work very well once the coefficients start getting a little bit complicated. So try those things for tomorrow. I will post the PDF and the video as usual, and we will pick up here next time. I will see you guys in the next one.